Good day, class. In this lesson, we will learn graphing rational equations. Notice how I've written our given equation in function notation. So I know it's a function. In fact, I anticipate rational behavior because I see that numerator denominator, my numerator being the quantity x minus 1, my denominator being the quantity x squared minus 1. So with that, knowing it's a function, knowing it's rational, there are some elements about rational functions that I really need to consider if I'm trying to graph the equation. So here, I want you to be thoughtful about finding the symmetry, any intercepts, any asymptotes, and potentially holes, and also test point. And use your test points, and you can sketch the graph of any rational function. So let's get started just thinking about some of these ideas. Starting with symmetry. Think about symmetry. Be thoughtful about what it means. You might find with the rational function, you might find symmetry about the origin. Here's an example of a rational function where we discover symmetry about the origin. And notice what I mean by symmetry. I can notice the graph. I see that pattern folding over point 0, 0, or the origin here. And then you can also see it in terms of points. Notice I'm at x is 1, y is 2/5. I'm just sort of averaging there 2/5, but bear with me. But if x is 1, y is 2/5, when x is negative 1, or on the other side of the x-axis, then y turns to the very same thing but the opposite, negative 2/5. So that's very critical. We can see that in the graph, as you saw, also in the table as you're looking at these points, and also in the equation. Here's an example of an equation where if I look at the negative x, or all negative x's, I can predict how my y's are going to turn out. They're going to be exact opposite. I have here the exact opposite equation that I had to begin with when I substituted a negative x. So you can always take your equation, substitute a negative x, simplify, and that will present in equation form whether you're going to have symmetry about the origin. Here I do in this sort of side example because you can see from my original function, f of x equals 4x divided by x squared plus 5. If I substitute a negative x and simplify, I end up with the exact opposite function. Now notice in this little sidebar example, I'm looking at a possibility of symmetry around the y-axis. So note, I'm kind of folding over the y-axis and I get the same graph. So the graph sort of shows me that symmetry. I can firm it up by looking at some points. Maybe if I'm looking at point 1 on the x-axis, 2/5 on the y-axis, if I look at the negative side of the x, or negative x, negative 1 in this case, I'm going to turn out to have the very same y value. Well, that plays out in the equation also. Here's a different equation, sort of a sidebar equation, if you will. I'm looking at the function f of x equals 4x squared all divided by x squared plus 5. If I observe negative x and how that y will fall out as a result, notice here what happens. I end up with the exact same function when I simplify where I started, because my y is always going to turn out exactly the same as when I substitute a negative x. So any negative x values or opposite x values are going to yield the very same y values when I have symmetry around the y-axis. So if our rational functions are predictable in that way, we're not going to anticipate any symmetry around the x-axis. That is not the behavior of a rational function. I can observe symmetry by checking the function at negative x. So notice now I'm taking my original function, the function I want to graph, and I'm going to substitute the negative x to see what happens. When I do that, I simplify, I discover there is no symmetry around the x or the y-axis or the origin, because I can see when I simplify my substitution, when I substitute negative x and simplify, I do not get the original function. I do not get the opposite of the original function. I get something completely different. So I see I do not have symmetry here around the origin or the y-axis, and we can also see that I have the little graph sketch there on the right hand side, so you can see actually a computer generated version of the graph of our function here. So we see there's no symmetry. So that sort of gives you just a quick rundown of what we're dealing with when you're looking for symmetry of a rational function. Let's move on and take a look at intercepts. Before I talk about the intercepts of the function we're graphing, just remember what intercepts mean. If I'm touching or intercepting the y-axis, I can be sure my x value, my x coordinate is 0. And if I am touching or intercepting the y-axis, the x-axis, if I'm intercepting the y-axis, my x coordinate is 0, and if I'm intercepting the x-axis, my y coordinate is 0. I can be certain of that. If that's the case, let's go ahead and intercept these axes algebraically. I'm going to look for the x-intercept of my function, so I'm going to let y be 0 because that's the only possible way I can get the corresponding x value for my equation, by letting y be 0. So I substitute a y as 0, I solve for x, and I discover that x is 1. And so I see, oh, when x is 1, y is 0. That is an intercept, an x-intercept. But I observe where that point might be, and notice I'm kind of ahead of us here because I've already sketched a graph because I want to discuss that the graph while we're working on some of this. But it's funny how the algebra gives me a point, but if I actually substitute x is 1 into my original equation, I'll get a 0 in the denominator. That is the reason this point is not on the graph. In fact, when we study asymptotes, you'll sort of see that. So in this case, I have to throw out this intercept. It doesn't actually make a true statement in my original equation. That point does not live on this graph. But I can also observe the y-intercept. Notice how when I'm touching the y-axis, x is 0. The x coordinate is 0. So I'm going to check. I'm going to ask myself, when x is 0, what is y? I'll solve for y here, and I discover y is 1 when x is 0. Therefore, there's a point on this graph I expect when x is 0, y is 1. And I discovered that actually is on the graph. So this is an intercept. So in this example, we do not have an x-intercept, although we do have a y-intercept here, which occurs at x is 0, y is 1. I also want to take a look at the asymptotes of my function, those lines where the graph will never ever touch. To discover the vertical asymptotes, I need to check the zeros of my numerator and the zeros of my denominator. To check the zeros of my numerator, I'm just going to take my numerator, set it equal to 0, and solve. And obviously, to check the zeros of my denominator, I'm going to set that equal to 0 as well and solve. Wherever my zeros appear in the denominator and do not also appear in the numerator are going to represent my vertical asymptotes. Notice I have a vertical asymptote at x equals -1 because this 0 does not appear in the numerator, although it appears in the denominator. So I can expect a line which I see has appeared here, which this graph will never touch. However, if I do have zeros that appear in both the numerator and the denominator, I can suppose those are going to be any holes I might have in the graph. So this graph has a hole at x equals +1, and we can see that if we try to substitute +1 into our original function, we would get a non-real number. We can also check for our horizontal asymptotes. Super important to discover if the degree of our numerator is greater than the degree of our denominator, then we will not have any horizontal asymptotes at all. If the degree of our numerator is less than the degree of our denominator, we will have a horizontal asymptote at y equals 0. And if the degree of our numerator is equal to the degree of our denominator, we will need to observe the leading coefficients of both the numerator and the denominator to determine what fraction we can use to represent our horizontal asymptote. In this case, however, the degree of the numerator is less than the degree of the denominator, so we know our horizontal asymptote occurs at y equals 0. The final thing you want to do is test points. Pick some random values of x, substitute them on either side of your asymptotes, and test those points and find the corresponding y values, plot them, and you'll discover your curve will play out very beautifully. Keep in mind that the graph is here, so in order to sketch the graph, you want to observe symmetry, intercepts, asymptotes, possible holes in the graph, and test points.